Here I have the graph of two different functions. One is the function x squared plus y squared, and the other is 3 minus x squared minus y squared. And the way these functions interact is that they have an intersection, and that inside of that intersection is a volume. And my question is, what is the volume of that region, this region in between these two different surfaces? In this video, we're going to talk about finding volumes of regions like this via triple integration. Integration where I'm integrating with respect to z and y and x. Now, the first thing I want to figure out here is what actually is the intersection, not just the region in between these. But if I look at this, it appears that there is a circle where these two different surfaces are going to intersect. Indeed, if I take the f1 and the f2, these are the z values, and I set them equal to each other, then what I'm going to get is this equation that x squared plus y squared is equal to the 3 minus x squared minus y squared. If I then add x squared plus y squared to both sides, divide out by the 2, what I get is that x squared plus y squared is 3 halves. But x squared plus y squared equals 3 halves is just the equation of a circle. Indeed, on this picture, we have this circle of intersection, a circle of radius, the square root of 3 halves. I can also imagine that I'm looking straight down on this, and that's going to give me in the domain, just again, this equation of a circle of radius, square root of 3 halves. So when I think about this volume and trying to compute it, my first observation is that the volume is entirely constrained within this particular boundary circle. So that the x values and the y values, when I try to figure out what those limits of integration should be, well, I'm going to get those values from this boundary circle. Okay, but what about the entire volume? Here's my strategy. I want to think of this as a triple integral. This is kind of long and messy, but what I have here is an integral of the function 1, dz, dy, dx. And then my z integral has two different limits of integration, the bottom and the top function, f1 and f2. The y integral is going to have limits of integration as well. These are functions of x. And then the final x integral on the outside is just going to be evaluated between two different numbers. And so my final result will be a number. The way I think of this as being a volume is that I'm adding up a lot of little volumes dz, dy, dx. If I take this large volume and break it up into all these little individual components, then I add up all of those components, I get the total volume. The integral signs are just a fancy way of saying I'm going to add up all of these small little pieces in the limit as the n is going to infinity. So the real goal of this video is coming up with all of those limits of integration. If I make this a bit more transparent, what we have is that the integral with respect to z is you choose some x value, you choose some y value, because we're going to integrate those later. So some x and y value. And then integrating with respect to z means that at that fixed x and fixed y, you have this vertical change. So I'm going to put this line, which I imagine really having a very, very small area and then some substantial finite height to it. And the bottom height of that is just the f1, and the top height of that is the f2. So to evaluate this, all I have to do is just, well, substitute it in. The equations that I knew, the f1 and the f2, were going from x squared plus y squared up to the 3 minus x squared minus y squared. So that's what that little vertical strip is doing. Okay, so I get that for every x and y. Now I want to integrate with respect to y. So that is, this little vertical strip that I have, I want to go and send it down a lot of different y values. So then I get something like this. That vertical strip has moved along for all of the different y values where x is, again, some specified value. So I think I plugged in x equal to 0.3 when I programmed it. And so I get this slice at x equal to 0.3. And as a result, you have this little region. That's when I integrate with respect to y. Okay, but what should the limits of integration with respect to y be? If I take this picture, and I look down at it from the bird's eye view to see just into the domain of x and y, what this strip that I'm doing when I integrate with respect to y is, well, it just looks like this. I have that circle in the domain, and after I integrate with respect to y, I get a vertical line. But in the domain, this was an equation of a circle. So the top half of it's given by y equal to the square root of this radius squared, the 3 halves minus x squared. And the bottom half is the negative of that, negative of square root of 3 halves minus x squared. So I can then return And what this is going to give me is it's going to give me this g1 up to g2 is nothing but the square root of 3/2 minus x squared with a negative up to the square root of 3/2 minus x squared with a positive. And then I take this combined slice, so the z value is changing and the y value is changing, gives me this sort of weird two-dimensional looking thing. I imagine I change that as I change my x values. My x values are also going from the extreme ends of the circle, so they're just going between the minus square root of 3/2 up to the plus square root of 3/2. This is now an integral, and we've done the hard conceptual part of figuring out what the limits of integration are, and after this, it's just a procedural process of evaluating it, which I will leave to you. One observation about this is that as I integrate first z, then y, then x, the z limits of integration are functions of x and y, and when I integrate, I get rid of any z's, only x's and y remain. Then the middle integral, the one with respect to y now, the z is gone, but the y's can be written in terms of x's still, so my limits of integration are functions of x. I integrate with respect to y, and I get rid of all y's, now it's just x's, and then the final integral, the one with respect to x, has new numbers in its limits of integration, so you evaluate that and you get a number out. By the way, the specific choice of doing dz, then dy, then dx, I didn't have to do that. It was convenient for us in this particular case because I had that the z was specified to be two different surfaces, so it made sense to integrate those first. However, if I had given you different sets of information, sort of by a generalized Fubini's theorem, you could do this integration in any order that made sense to you. Nevertheless, we have the volume of a region using triple integrals.